Welcome to Lecture 8 of Introduction to Computer Architecture. I'm Simon Moore, and today I'm going to tell you all about memory hierarchies. So the motivation for this lecture really stems from an observation back in the 1940s that I talked about in Lecture 1. So if I just read this quote from this old publication: ideally, one would desire an indefinitely large memory capacity such that any particular word would be immediately available. We are forced to recognise the possibility of constructing a hierarchy of memories, each of which has greater capacity than the preceding, but which is less quickly accessible. Okay, and this problem is very much with us today. We can't make a really fast memory that is also very large, and it's a problem of physics. You know, if it simply takes time to get data from further away. So what we tend to do is build a hierarchy of memories, and we have a very sort of cartoon-like notion down on the bottom. So here we've got the idea of having a processor core with separate instruction and data caches, in order that we can do, instruction fetch and memory access concurrently, rather in parallel in our pipelines. These are usually backed by further levels of caching. Here I've just drawn a second level unified cache. So this L2 cache would hold both instructions and data. And that's then backed by DRAM, and in fact if we run out of DRAM we might even store some of the memory on disk. Okay, and the idea here is that the L1 caches are small, they're physically small, so we can have low latency access, which is necessary to make von Neumann style processors run quickly, because we soon get these sequential dependencies between accessing memory and needing to use the result. Since those caches have to be quite small, usually just a few kilobytes, we then use a much larger L2 cache. That cache may well be on the same chip, but it'll be physically much larger, and it will probably take several clock cycles, for example 9 or 10 clock cycles to access. And then we've got off-chip DRAM, and that's going to be typically hundreds of cycles of access. And then disk, if it's non-volatile, then you'll still be talking of thousands and thousands, if not millions of cycles, and if it's magnetic disk, even more so. Let's now look at memory technology characteristics. So we've got SRAM, which is typically on the processor chip for on-chip caches. SRAM, so static random access memory, is low latency, but the latency is proportional to size. So if it's a very tiny little memory, you might be able to access this in a single clock cycle. If it's a much larger memory, it may well take longer. It's going to be very high bandwidth. If it's on chip, we can have quite wide data widths, and in particular when we're moving data between caches, we might move several words at a time. The size is limited by the chip area to a few megabytes, but we can have many SRAM blocks, so we can also have lots of, sort of parallel accesses going on. Also, the read-write size can easily be byte level, and that's very useful at this level of the abstraction. Then typically we still use DRAM, so dynamic random access memory, off chip. The access latency can be hundreds of clock cycles, and it's still usually pretty high bandwidth. So if you've got something like DDR4 memory, it's got a 64-bit bus, and you can actually get of the order of 25 gigabytes per second, which is pretty good. Although it's still not as fast as on-chip memory, which I indicated, could be around 64 gigabytes or possibly more. So reads and writes have to be in small blocks for DRAM. Things are transferred as bursts. A common burst size is 64 bytes per transfer, either for reads or for writes. And then we've got some form of disk, either magnetic hard disk or flash memory, and we tend to use that for page-based virtual memory. And I'm going to talk about virtual memory much more next lecture. So this is typically high latency. For a magnetic disk, you've actually got to wait for the disk platter to spin around under the disk head, and it could easily take 3 milliseconds to access that data. And it's going to be microseconds though if you've got modern NVMe based flash disk storage, which is a much faster interface than say SATA. The bandwidth though is lower. If it's over a SATA link for a magnetic disk or just a SATA based SSD, then it's going to be less than a gigabyte per second. On the other hand, if it's an NVMe based device that runs over PCI Express, then you're going to get tens, sort of 10 gigabytes or so a second. I think the upper limit's about 16 gigabytes per second, but quite hard to reach that. Reads and writes tend to be in larger blocks, of the order of 512 bytes a time, and that tends to be needed because these devices also require extensive error detection and correction codes, and in order to have those codes, a lot of coding, you tend to need to work with larger blocks, should I say. Caches really work because they can exploit the principle of locality. So programs access a small proportion of their address space at any given time, giving rise to the following statistical properties. So we have temporal locality. So items accessed recently are likely to be accessed again soon. So for example, instructions in a loop, we're going to keep fetching those instructions. We'll also have loop counters and other repeatedly used variables. We also have spatial locality. So items near those accessed recently are likely to be accessed again soon. So for example, you might have a loop that is accessing an array of data, and if you access one element of the array, there's a really good chance you're going to access the next, and so on. Spatial locality tends to play quite nicely with DRAM bursts and the idea that we need to fetch chunks of data into memory. In other words, if we need to go to DRAM to fetch some word of data, then we will fetch all of its neighbours all in one burst, because it's quite likely that the program is going to read the neighbouring data anyway, and we'll get efficiency because we get one burst, gives us a big chunk of data. Let's look at some of the cache terminology. So the cache is a memory that holds recently used data so that it can be more rapidly accessed. In other words, it gives you very low latency access to that data next time you use it. And the idea is to really try and sort of alleviate or mitigate, rather, the von Neumann bottleneck. A cache hit is where data is found in the cache, so we can just read it. A cache miss is where the data is not found in the cache, so it has to be fetched from the next level in the hierarchy. And that may well be another cache in the hierarchy that just happens to be bigger than the cache we're considering at the time. And then the miss rate is simply the number of cache misses divided by the number of memory accessors. And for caches to work well, they often need quite a low miss rate. Let's look at a very crude, direct mapped cache model. So this is kind of the, if you like, probably the simplest cache you can build. So here we've got an address that we're going to load from, and we're going to take some sort of hash of that address and to get a cache address. Okay, so this cache might just be a few kilobytes of SRAM. And that hash might be very simple in that we may just use a few of the bits out of the load address. So we would then use that cache address, that hashed value, to read to see if the data is available, and also associated with that data is a tag, which is actually the full address of where that data is stored in the DRAM. If the tag matches the load address, then we say that we've hit in the cache, and we can then read the data out. Okay? But let's see how we can build a slightly more sophisticated and more efficient cache. Let's look at a simple direct mapped cache, the sort of thing that you would actually use for real. So what optimizations do we need to do? Well, storing the address as a tag for every data item, every data word, is going to be enormous overhead. You could easily double the amount of storage that you need. So what we're going to do is amortize the cost by storing several data items per tag, so several words. So for example, and this gives us what's called a cache line. Okay, so this might be 4 machine words in memory, 4 contiguous words in memory. And this links nicely with the spatial locality idea, and also with the idea of DRAM bursts, so that if we need to fill a cache line, we can do so by just reading a burst out of DRAM. The actual hash function to do the index into the direct map cache is usually just some bits out of the instruction, and in fact we use the lower bits as a byte or word select. Then we've got the index bits, and then the upper address bits are the tag. So let's look at this graphic. So in this figure we have a simple direct mapped cache, which is basically an SRAM block that contains a tag, a valid bit, and 4 words of data, if you like, as the sort of columns in the SRAM, and then the rows of every entry in the SRAM. If we then have the address, the actual memory address, then from that memory address we extract an index, which basically gives us the cache address into that SRAM block. And this is basically our very simple hash function. That points to a particular line in the memory. We read that out, and so we get the tag, the valid, and the 4 words. We use the byte and word select to select which bits of data we want, and we use the upper bits of the address to compare with the tag field, and this basically ensures that we have actually read the correct data and it is unique, because obviously we can get hash collisions on this memory because there are many memory addresses that map to the same cache index. Let's have a think about cache line size considerations. So larger cache lines should reduce the miss rate because we actually get better spatial locality. However, there's a bit of a trade-off. In a fixed sized cache, then larger cache lines means that we have fewer of them, and so you sort of get more competition if you've got lots of different regions of memory to cache, and so that can increase the miss rate. We also get problems of cache pollution for larger cache lines, in that we're likely to read in, probabilistically we might read in more data that we'll never actually use, and so that's inefficient. So there is a real trade-off here. Also, there could potentially be a larger miss penalty, so we can override the benefit of reducing the miss rate. the reason for the larger miss penalty is that, you know, every time we get a cache miss, we've actually got to fill the entire cache line, and you know that's just a lot more data to fetch. Now there are techniques to try and mitigate that a bit, and in particular, if you get a cache miss, not only do you say, I want to load this cache line into my cache, please, but you usually say which word you need first, and that helps with the miss penalty. So on a cache miss, what do we do? Well, obviously on a cache hit, the CPU proceeds as normally. You know, if it hits in the first level cache, great, you've got the data, not a problem. If it misses in the cache, then we have to stall the processor pipeline. We have to fetch the cache line block from the next level of the hierarchy, and if it's an instruction cache miss, then we typically have to restart the fetch process. And if it's a data cache miss, we sort of have to complete the data access. There are different ways to handle writes to the cache. So if we write something to a cache and the cache block is already in the cache, in other words, it hits in the cache, then that's pretty simple. You know, we just update the line in the cache. But of course, we then have to remember that the rest of the memory hierarchy is inconsistent with that write. So one approach is to do what's called write through. So basically, write propagate all the way down the memory hierarchy and potentially all the way to DRAM, although it might stop in the last level cache, in other words, the cache just before DRAM. So the problem with doing that, however, is obviously if it takes a lot of cycles to do a write further down in the memory hierarchy, and in particular if it's going to go to DRAM, it could easily take 100 cycles, then that could have a major impact on the processor, because if we have to wait 100 cycles every time there's a write instruction, that would be just terrible. And in fact, there's an example here. You know, if our current cycles per instruction is 1, then 10% of our instructions are stalls, and a write to memory takes 100 cycles. The effective CPI would become 11, which is just ridiculous. You know, 11 clock cycles, basically 11 times slower. So one solution is a write buffer. So that holds the data waiting to be written to memory, so that basically the processor can continue working, and the processor then only stalls if the write buffer is full. And of course this will work fairly well. Imagine we just have to write all the way through to the last level cache in order to ensure consistency. Then that might be 20 clock cycles, and in which case we might be able to hide the latency. Another approach is write back. So on a write hit, we just keep the data in the cache line, and we basically keep track of whether the line is dirty, which is a bit of an odd phrase, but that's what's used in the literature. So if a write has happened to a cache line, so it's got new data in it, it's marked as being dirty, which I think is an odd term, but that's what people use. And when a dirty block is replaced, in other words, when we need to replace that cache line with some new data, then we ensure that information is written back to the next level in the memory hierarchy. And of course we might use a write buffer at that point in order to allow the replacement cache line to be first be rapidly inserted into the cache, and then the writing stuff through to the memory will happen later. Of course, the next question is, well, what happens on a write miss? And we've got a couple of alternatives here. There are a couple of alternatives for write through. Well, we could allocate on miss, so we could fetch the cache line and then perform the write to the cache line and then write it through. Or we could just write around, so we basically don't bother to fetch the cache line at all. We don't allocate, but instead write the data to the next level in the hierarchy. For write back, we have to allocate on a miss. So we fetch the cache line to avoid having a cache line where some words or bytes are invalid, and then we basically update the cache line in place. Now let's have a look at alternative caching strategies. So we've just seen the direct mapped cache. Now let's look at a fully associative cache. So the idea here is that we use just the lower bits of the address as a byte or word select, and we use all of the upper bits of the address as a tag. And here we're going to look at the tags in memory and actually in parallel compare every tag with those upper address bits. Okay, now remember that hardware is inherently parallel, so all those comparisons can be done simultaneously. Nevertheless, having all these sort of comparators is quite a cost. So actually fully associative memory is generally just too expensive if we've got a larger cache memory. However, for small memories it can be quite efficient, and we will see when we talk about virtual memory in a later lecture that the translation look-aside buffer, which is also a form of cache, that in fact often is fully associative. One of the advantages though with a fully associative cache is that you can place a cache line anywhere in the cache, and this actually gives us flexibility with the replacement policy. So let's do a quick comparison with direct mapped versus fully associative caches. So circuit area, a direct map cache for an ASIC certainly uses less circuit area than a fully associative cache, although actually all those comparator operations we need to do, if you actually design the cache at a transistor level, it's not as bad as you might think. On FPGA though, there are typically no fully associative memory blocks provided inherently by the FPGA fabric, so you basically got to fabricate it out of lookup tables and D flip-flops and things, and that ends up being just enormous. On the other hand, FPGAs do have block RAM, so they have lots of small SRAM blocks, and they're ideal actually for making a direct mapped cache. Let's think about efficiency. So fully associative caches tend to have a higher hit rate than direct map cache that stores the same amount of data, primarily because we can reuse cache lines in a much more efficient manner. An alternative approach is to combine the efficiency of a direct map caches with the higher hit rate of the more associative cache using a set associative cache. So logically, a set associative cache is basically made up of some number n direct mapped caches. Okay, so read look in all n caches for data, and thus the cache is n-way associative because there are n places where we could store the cache line. So remember, with a direct map cache, there is only one place in the cache where you could normally store the data, because you're just using some bits of the address as basically a hash function into that memory. But as I said, with a set associative cache, we actually, rather than reading one cache line, we read n cache lines, and then we compare the tags and figure out actually which of these n ways is actually holding the data, or not in the case of a cache miss. Set associative caches turn out to be a really good compromise, and they're very widely used on commercial cores. So here's some stats for some current cores. So fairly high performance Intel Core i9. It's got 14 cores, And so there are 14 L1 instruction and data caches, and each of them is 32 kilobytes, and they're 8-way set associative. Then there's an L2 cache for each core. So basically there are, let's just get this right, there are actually 28 L1 caches in total, because there's 14 instruction caches and 14 data caches. Then there's a unified L2 cache, so basically each of the 14 cores has one L2 cache, and that is 1 megabyte 16-way set associative. And then actually on this processor there's then a last level cache, so all of the L2 caches feed into the enormous L3 cache, and that is 19 megabytes and 11-way set associative. These are actually kind of interesting numbers, and in particular if you look at all the L2 caches, because we've got 14 of them, we've actually got 14 megabytes of L2 in total, but distributed among all the cores. And we've actually only got, we haven't got that much more L3, but that is shared, and so this is trying to exploit different access patterns, or maybe one or two of the cores just happen to be accessing large data sets and hopefully the other cores are not, or there's a lot of shared data that would be held in this large L3 cache. In contrast, it's interesting to look at a Raspberry Pi 4, which has an ARM A72 on it. It's got 4 cores. Remember, this is a much cheaper chip, much lower power, and yet actually some of the basic cache characteristics are not so different. Interestingly, it has a bigger instruction cache than the high-performance Intel Core, which I find really amusing. It's also 3-way associative, so it's obviously 3 blocks of 16 kilobytes. The data cache is actually smaller, it's 32 kilobytes and just 2-way associative. And then there's an L2 unified cache among all the cores that is a megabyte in size and is 16-way associative. Now let's look at the replacement policy. In other words, if we read something in the cache and we miss, and we need to go and fetch that data from the next level in the memory hierarchy, the question is, what cache line gets replaced? In other words, what cache line do we have to obliterate in order to put the new data there? Of course, in a direct mapped cache, there is no choice. Okay, we can only map data to one place in the cache. So if we miss at that line in the cache, then that cache line has to be replaced. In a set associative cache, and also in a fully associative cache, we actually have choices as where we can put the data. So first and foremost, in a set associative cache, you will see if one of the ways is not valid. In other words, there's just no cache data there at all, and of course you prefer that. Because there's no data there, we're not going to have an impact on any later code needing some data that we might obliterate. Otherwise, we have to make a choice, and we have to remove some data from the cache in order to replace it with the new data, and then we have to make some choices. So quite a good one is least recently used. So we choose the way that that has been unused for the longest, and that's fairly simple to do for a 2-way. It's manageable for a 4-way. It starts getting a bit harder if the more ways you have, because basically you've got to keep track of statistical properties of usage for all of the cache lines, and there's various tricks to make it efficient, but still there's a bit of an overhead. Nevertheless, it's quite often used. Another approach, if you want something sort of simpler, is to do not last used, and it's sometimes referred to as a sort of pass the hot potato algorithm. So the idea here is every time you get a cache hit, in a way, if that particular cache line has is holding the hot potato, or the bit saying you're likely to be replaced, then it says, "Oh no, not me. I've just had a read, so I'm holding useful data. Therefore, I'm going to throw the hot potato to the next cache line." And actually, this sort of approximates least recently used, because the hot potato, or the flag, tends to end up on the cache line that is not being accessed very often. And finally, another approach is just random. We just randomly choose which cache line in the way to replace, and it's fairly simple to implement, and it tends to avoid pathological cases. So, you can, with some of these replacement algorithms, run into pathological situations where you fetch some data, you start to use it, you have to fetch some other data, and then you end up overwriting the data that you've just recently used, and then the code comes back to it, and you get yet more cache misses. So there's sort of pathological cases. Another trick we can use is to add a mechanism called a victim buffer or victim cache. And here what we're going to do is augment a direct mapped cache with a tiny fully associative cache or buffer. And I guess you could also do this with a set associative cache, but there's usually enough associativity in the set associative cache that you don't need to bother. So this is really aimed at direct map caches, where you want to add just a little bit of associativity. And if we've just got one, fully associative cache line, that's very little hardware. And when we evict the cache line from the direct map cache, it kind of gives that cache line a second chance. And it actually eliminates some of the pathological cases of a direct mapped cache. And it tends not to be as effective as a set associative cache, but still it helps. Let's just think about what some of these pathological cases might be. Imagine we've got a 32K direct mapped cache, and imagine software is just trying to do something simple like reading two arrays that are both 32K in size, and it's just reading every element of these two arrays and summing them up. Well, you'll read a value from the first 32K block, call that block A. Then you'll do a read from block B, and of course when you read from block A, you'll have fetched the data into the cache, and when you read block B, you'll actually end up evicting the cache line from A in order to install the cache line for B. And that's a bit unfortunate, because if you're reading sequential sets of words, you lose the spatial locality, because obviously when you did the cache fetch, you will have fetched say 4 words at a time, and ideally you would read all of those 4 words before the cache line gets evicted. If you'd installed the victim buffer, it would get around this problem. Let's look at the sources of misses. So we have compulsory misses, and these are often referred to as cold start misses. So this is basically, it's the first time this data has ever been read, and so it's missed, and therefore you've got to fetch it into the cache. We can also have capacity misses, and this is basically where the working set of the algorithm is bigger than the size of the cache, and one of the problems you can then see is that you have to remove a block from the cache which is later accessed again, and so that's a bit of a problem. And really all we can do there is rely on hopefully getting that data fairly quickly from another level in the memory hierarchy. We can also have conflict misses or collision misses, and this really happens in a non-fully associative cache. So if we've got a set associative cache or a direct mapped cache, we can end up with competition for entries in the cache line. And as I said, this is particularly a problem with direct map caches. And so typically we say we've got a conflict miss if it wouldn't have occurred if we had a completely fully associative cache where you can, map cache lines anywhere in the cache at all. So as always in computer architecture, there are design trade-offs, and sure enough there are design trade-offs with caches. There is no way of designing the perfect cache. So let's just look at some of these design changes you could make. So you could increase the cache size, and the effect would be to decrease the capacity misses. However, it may well, in fact it's very likely, to increase access time. We could increase the associativity, and that would decrease the conflict misses. However, that's likely to increase the access time as well. We could increase the cache line size without actually increasing the size of the cache itself. So in other words, if we increase the cache line size, we have fewer cache lines in the cache. That's likely to decrease compulsory misses because we tend to get better spatial locality. However, it increases the miss penalty. For very large cache line size, it tends to take longer to populate the cache lines, and that's also a problem. So at the end of the day, we end up having multiple levels of cache. So we've usually got an L1 or a primary cache that's attached to the CPU. It's small, but it's very low latency. And in fact, the L1 caches are often such an integral part of the CPU, they're often designed closely together. Then you've usually got an L2 cache, and that services misses from the primary, from the L1 cache. It's larger and a bit slower, so lower latency, though it may still have the same bandwidth, but it's still an awful lot faster than main memory. And as we've seen, it may well be the case that you have an L2 cache associated with every single core, and then the main memory services the L2 cache, or in high-end systems we may have further levels of caching. In fact, I've even seen some systems with 4 levels of caching. But as I showed you on the i9, the Intel i9, that's got an L3 cache which is quite large, and that basically sits in front of the DRAM. The cache closest to the DRAM is usually called the last level cache. Let's have a look at an example multi-level cache to see how effective multi-level caching can be. So imagine we've got a processor with a CPI of 1, which is fairly modest for a high-end processor, but let's see if we can manage to hit a CPI of 1, and say the clock rate is 4 gigahertz. So we had a miss rate per instruction of about 2%, and the main memory access time was 100 nanoseconds. So with just an L1 cache, the miss penalty would be 100 nanoseconds divided by the cycle time, which is 400 cycles. Okay, and that would give us, if we assume that we just get a single cycle access to the L1 cache on a hit, we then get the effective CPI as follows. So here, of course, we always access the L1 cache even if we miss. Okay, so it's always going to take us 1 clock cycle, and then if we miss, then we've basically got the miss rate of 2% multiplied by the cycles, and that gives us a CPI of 9, which is pretty horrendous. Now means our processor's going 9 times slower. So let's add an L2 cache with an access time of 5 nanoseconds and a global miss rate to main memory of 0.5%. So the L1 cache miss with an L2 hit is 20 clock cycles. Okay, so it's a 5 nanosecond access time, and that, at a 4 gigahertz clock means that 5 nanoseconds is 20 clock cycles. And the L1 cache miss with an L2 miss is going to have that extra penalty of 400 cycles, as we've seen before. So if we then work this through, we get a CPI of 1, which is L1 hit or miss. It's just the L1 access time, and then we've got a 2% chance of us getting the data in 20 clock cycles. Otherwise, if we miss in the L2, then we've got to go and fetch data from main memory, and that's only a 0.5% chance, but it's 400 cycles. So that improves the CPI to 3.4 and improves performance significantly. However, should be bear in mind the CPI of 3.4 is still pretty awful. So if you look at all these stats, well, what could we do to improve things? Well, obviously, if we can design the caches so we get a much lower miss rate, that would help. The actual memory access time is down to the physical properties of the circuits. So there's not a huge amount we can do there. So yeah, it's a real challenge. The other thing we can try and do is allow the processor to tolerate some of the misses a little bit better. So for example, if we missed in the L1 cache but hit in the L2, it might be that whilst the cache is servicing the miss, rather than the processor stalled, waiting on a load instruction, ideally we'd have the processor continuing to try and do other work until it really, really needs the data that will come back from that load instruction. Now, there's actually a lot of other issues in caching, but we're not going to cover them, all of them, in this course. But just so you've got a little bit of an idea of some of the topics we're not going to do properly, there's prefetching, which is actually very important and will be covered more in comparative architectures. So here we identify memory access patterns to further improve cache performance. So, doing things like spotting sequential reads to ensure that the cache prefetches the data before the processor actually realizes it needs it, basically. That can really help. Another thing we've not talked about yet is context switch penalty. So obviously, in a modern operating system, you will context switch between applications to share the processor resource between different applications, between different threads. Unfortunately, of course, though, every context switch has a major impact on the temporal and spatial locality properties that the cache will observe. Because as soon as you've done a context switch, you're working on a different thread, which is likely to have different code and different data. And so you tend to expect that an awful lot of the data that's currently in the L1 cache will be clobbered. And often a great deal of the data in the level 2 cache as well. So every time you do a context switch, there's major cache impact and major performance degradation. And the final one on this slide is coherent caches, which we need for multi-core systems. So quite often, if it's if it's a multi-core system on one chip, then we have a last level cache, say an L3 cache, which caches stuff directly from the DRAM, and that's shared among all the cores. But then we've got L1 caches and L2 caches that are often specific to particular cores, and we need some sort of protocol to ensure that if one core writes some data that another core wishes to consume, that data is forwarded. And that's quite a tricky problem, and is something that we're going to talk a little bit more in the latter part of the course when we talk about systems on chip. Right, let's wrap up this lecture. So to summarise, the physical constraints prevent construction of a large low latency memory. So we are reliant on having a hierarchy of memories to approximate a large low latency memory, since this is critical for high performance on a control flow processor. Caches exploit temporal and spatial statistical properties of memory accessors to store data likely to be used close to the processor. However, it should be noted this really isn't a panacea. The last level cache often has 80% dead data. In other words, about 80% of the data in that cache will never be accessed again before it is evicted. So that's pretty wasteful, but that's where we are. Set associative caches are widely used. They prove to be a good balance between the simplicity of a direct mapped cache while giving some of the associativity of a fully associative cache. And finally, I think it's interesting to think that, it's ironic that we devote so many transistors to moving and storing data. We spend a huge number of transistors on caches and predictors and all sorts of things, and really very few on the actual computation. And this is another sort of Turing tax, if you like. Thank you.